All right, good morning. This is Sasha. I am making this video because I am away today. Um, it's morning here for me, but by the time you view this, I don't know. Who knows what time it'll be? But we got a few things to look at before exam day, which is, well, in my reference frame, it's tomorrow. For you, again, I don't know. Maybe you're very silly and looking at this like 5 minutes before the exam. Either way, the fact that you are looking at this means that you are trying to prepare, which is good, and that's good on you. So we have a few things to cover here before the exam kicks off. So for those of you that have been going to my sessions, you've been doing a good job showing up, participating. And for those of you viewing who haven't been coming to the sessions, join up. We've been expecting you. No, but definitely stop by. This is a good way to prepare yourself and just, know your way around. You don't have to come and answer every question correctly. Just engaging with this content solidifies it and reinforces it come exam day. So, without further ado, let's look at a few minor points that we should talk about. So there's more than this, but this is what's going off the top of my head. So first of all, we have velocity versus velocity. Okay, what do I mean by that? I am so glad you asked me what I mean by that. This is what I mean by that. Okay, so let me just get my pen. All right, so let me make sure this is working. Okay, cool. So let's look at this problem. First of all, you got to know which function to use when. In this case, it's given to you, but I just want to make something very clear right now. When you're given a function with a wave, it's a wave function because it has this trig term here, and it has terms inside that are dependent on time. That's like the bare minimum. How do I know that this isn't simple harmonic motion? Well, simple harmonic motion isn't talking about x of anything. Okay, simple harmonic motion takes time as a parameter and spits out x. So SHM is going to be like a cosine omega t is equal to some x value. It's usually x of t is equal to that. What does this mean? This means you give me time, I give you place. Place being somewhere in physical space that the thing is oscillating in. So let's say this is time, t, and this is x, where it's not actually moving up and down in real life. For all we know, it's moving horizontally. But x, being on the y-axis, just refers to this is out 3 meters, or this is out 2 meters. I'm not putting those down, but I'm just giving examples. That's really what this wave function is describing, and that's simple harmonic motion. Why am I bringing this up? Because that's not what we're given here. We have a few wave functions to deal with in this chapter. Watch this, look at this. Boom, okay. So, knowing which one is being used is helpful. Okay, I talked about this during one of my sessions, but basically, if you're given something with simple harmonic motion, we're talking about a cosine. This is for position x of t is equal to a amplitude cosine omega t plus maybe a phase constant if it's given, and its respective derivatives. So in this case, we have a wave function describing y of x and t, which it's been explained this way a few times, but imagine a string being yanked up and down like that, and you have a point on that string, right? This could be a jump rope. I'm not a jump roper myself, but if this makes sense, you can think of it that way. As this wave travels through this string or jump rope, this point isn't going anywhere. This one right here, all it's doing is moving up and down and up. like that, like so. So all that function is telling you then is y x of t. I don't even have to draw the function or write the function. It's saying you give me time and x location, and what that asks is where along this string in the x direction am I? Am I here? Am I here? Am I here? And then time asks, okay, well, which part of the motion is the wave in? Because it's not just standing like this, unless you're talking about standing waves. It's traveling through and oscillating. So you give me time and x location along the string. I give you the y position or height of the point on the string. Of point on string. And wondering, well, Sasha, why are you talking about this crap? I already knew this. Well, it's important to distinguish between the two because come exam day, again, you don't want to confuse wave functions. That is not ideal, okay? So without further ado, we're going to talk about this one real quick and this problem. There's something I want to touch on, and it was the first point in my slide. Velocity versus velocity. Okay, we're given two things, right? And I'm sure you remember this formula. Or if you don't, it's okay, but this is handy to have on your note card. Right, we have V is equal to omega over K. This is wave number, and it'll usually be given to you, but if not, you have formulas for it. Omega is angular frequency. I'm just going to write it as angular F, and this is transverse velocity, okay? So, again, I'm just going to go back to this diagram, right? We got wave, and 1 second, the wave might look like that. Next second, the wave, this point right here, has shifted, not physically, not the point on that string, but the energy that the wave is carrying has shifted, and that part of the string has gone down a bit, and the wave has moved essentially to the right. Okay, and how fast that happens, how fast this thing went from here over to like here, further along the x-axis, that's what this v is equal to omega over k is talking about, right? You don't want to confuse this with taking the partial derivative of the y position, because what happens if, okay, we have y x of t, and like I mentioned earlier, this is position on the string, but up and down direction. This is talking about a physical position on the cord, on the connective element that is being bobbed up and down. It's saying, okay, well, it's moving up and down. I can tell you its position if I know time and if I know the location along the string horizontally, right? But that is not the same. Taking the partial derivative of that to get v of x and t, where you're going to have to do del t x, excuse me, y, go away, y x t, right? That is not the same as v is equal to omega over k. Okay, I know my notation here isn't brilliant, but this is how fast is that point on the string bobbing up and down. I can tell you where it is with these parameters x and t. Take the partial with respect to t, and remember, do not take your partial derivative with respect to x. This is not, if we're talking about this y of x and t function, x is not changing. You're not suddenly talking about this point. If you pick a point, if you pick a spot on this function in the x direction that you care about for y x of t, you're not going to change that point, right? That essentially, that's missing the point. Ha 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 ha. You're not changing which point you're talking about unless you explicitly say, okay, you know what, x was 0.2 meters. Now I care about what's happening at x is 0.4 meters. In that case, then yes, you're changing x. But you're taking the derivative with respect to time because you care about how fast this thing is moving up and down. You're given a position function, take the derivative with respect to time, you get the velocity function. That is physics 1 stuff. The partial derivative aspect of it is not scary, okay? I am literally just going to write something off the top of my head. So it's sine 3x minus 4t plus 7. Okay, this is the function. I don't need this extra parenthesis. You'll have to ignore that. But I have this function where this is a really nasty phase constant because it's not in, pi something, but it doesn't matter. Because when I go to take Vx of t is equal to del t y x t, then del t of sine of 3x minus 4t plus 7, right? I'm taking the derivative with respect to t. Okay, I don't care about you. I don't care about you. I mean, they're staying along for the ride, but really, all I'm doing is taking the derivative of the trig function. So I'm getting, first thing I'm going to write is cosine, okay? But don't forget chain rule. But it's not like every coefficient or number here gets pulled out, right? Like if I go back to just regular calc and I say sine of 3t plus 5 as an example, when I take the derivative of that, I'm getting 3 cosine, just pretend this is an x, 3 cosine 3t plus 5. What happened to 5? Well, it's treated as a constant, right? Because chain rule says you take the derivative of this entire parameter or argument, whatever you want to call it, with respect to t, and that's 3, right? Derivative of 5 is 0, and you're taking the coefficient off of the t. Again, this is just calc 1 stuff. But the reason I'm bringing it up now is because when you're taking a partial, you have nothing to be afraid of. You just treat this 3x as if it were a constant, like 7. Like this, right? So sine of 3x, that's just going to 0. That is just going to 0. As far as pulling out the derivative, right? Like when I'm doing chain rule, I'm saying, okay, well, what's the derivative of the inside of that function? 3x minus 4t plus 7. And this is why your calc teacher would always talk about the dt or dx with integration, because you want to know what you're taking your derivative or integral with respect to. You care about the variable that you're talking about, what is changing. So here, t, I'm taking it with respect to t, which means that the coefficient of t is going to fly out, but this goes to 0, it's like a constant, and this goes to 0, it's like a constant. So you end up with negative 4 cosine 3x minus 4t plus 7. Okay, and you also don't want to forget sines. Okay, if I take another derivative for a of x and t, now we're talking about how fast is the velocity changing of this point on the string, then what's going to happen? I'm pulling that negative 4 out again, and I get a 16, but then I get a negative sign, because the cosine changes to a sine. 3x minus 4t plus 7. It's very easy to trip up on the signs. And I'm not saying the trig function sign, I'm saying literally plus or minus sign. It's easy to trip up on that because you have so many things that are going on. You have a negative, usually, that's getting pulled out, and you have trig functions that are being differentiated and turned into other trig functions, and sometimes there's a change in positive or negative there as well. So keep track of your signs. If you need to make a little table and be like, okay, well, it was positive, but this happened and this happened, whatever helps you and whatever strategy works best for you. For me, I just take it one step at a time. I pull out the negative 4, and I'm like, okay, that negative just changed to a positive, but then I changed my cosine to a sine, so I get another negative. So we had negative 4 times negative 4 times, you could even say negative 1, and you get a negative, right? Negative times another negative is a negative. Okay. So pay attention to your signs. I was making a very long-winded point here, but I'm trying to say don't confuse your velocities. Okay. When you take the partial v of x and t, I'm just going to sum it up here. You are describing how fast this point on the string is moving up and down. You had y of x and t before, which told you where it was. Now you care about how fast it's changing that y position. V is equal to omega over k is telling you how fast it's moving this way or this way. Not the point on the string, but rather the wave itself, right? You don't want to think of the, like, let's say this is the string rope, right? And we have some point on this rope, and this thing begins bobbing up and down as a wave travels through it. Notice how I'm not saying the string itself is traveling anywhere horizontally. I'm saying the wave is traveling through the string, right? The string is an element that oscillates because energy is traveling through it. So if we care about how fast that wave is moving, the energy of that wave is moving through the string, then we say V is equal to omega over k, and you do all your calculations. So to sum it up, only take this partial derivative v of x and t, and I'm talking about these traveling waves. You might be asked about this, but if you are, don't confuse that with v is equal to omega over k. These are two very, very different things. This is in the x direction, and this is in the y direction. This is of the wave's energy, or the wave itself traveling. This is a physical point on oscillating element, whether it's a rope or a jump rope or a string. I don't care. I'm talking about a physical location on the vessel. Okay? So I hope that makes sense. So if we have any questions about that, you feel free to email me. I hope that explanation was somewhat clear. Again, it was long, but this is important. You don't want to confuse the two. Okay? So let's get rid of all of that with my nifty erasing features. My laptop flies everywhere. I got most of it there. Okay. So as for going through this problem, we're not gonna. I can if you want me to, but you should know how to do this. Essentially, I'm given an x position and a time for a function that takes x and t as parameters. It's asking me what is y with respect to the equilibrium position. And by the way, if you're ever asked that with respect to the equilibrium position's in the middle. So it's essentially saying, okay, well, if y equals 0 is equilibrium, right, then given an x and a t, I'm going to have y is somewhere not at equilibrium, potentially, right? If we're talking about this is really messy. Hold on, let me get rid of the, oh geez, hold on, give me a minute. I'm going to cut this out in the video, of course. All right, so wave, like this, that's a really crappy wave, not the point. Point is, equilibrium is in the middle, typically, and it's asking you, okay, well, at this point, x and t, somewhere along this wave, at some certain time, maybe I'm talking about right here, that is a vertical distance away from the middle. And what is that distance? That's what that question's asking you. So we can do it out real quick, okay? Y of x and t is equal to, I'm going to convert this to, what was that, 0.2 centimeters divided by 100. And we get 0.02 meters. I just, I had to check myself there, so I did a little skip. 0.002 meters sine 2 minus 3 plus pi over 16 sine of 2x minus 3t plus pi over 16. And that's about 6. I'm given x and t, and they are 4 meters and 10 seconds, okay? So you start to kind of see what this function is asking. It's saying, again, where am I on the string and what time is it with respect to when I started my stopwatch. Height of the string, respect to the equilibrium position. So all you have to do in this case is plug stuff in. Okay, we got 0.002 sine 2 times 4 meters minus 3 times 10 seconds plus that little phase shift, pi over 16. So we're here now. I paused, went and typed this into a calculator. This is Desmos, it's really cool. And I got this number. It looks a little scary, but we'll write it down and look at it. Just a very important point to make now. You see this? Radian degree mode, right? When I'm doing this, and I have a pi over 16 in here, unless you literally go and convert that to degrees and then plug this in, take this calculation in radian mode, or you're screwed. You're cooked if you don't do that, okay? You will get a bad number if you don't do this in radian mode. Why? Because when you look at that function, excuse me, when you look at that function, I'm just going to cover this real quick. You have some trig, and then you have, kx minus omega t plus phi. Okay, this is in radians per seconds, and I know it's multiplying something with seconds and they cancel, but radians, this is radians, right? That is the SI units on this function. So if you're ever taking sine of some inputs and there's a phase constant and whatever you have to deal with, take it in radian mode. Okay, that's very important, very, very important. And as for the answer that I got in Desmos, I got something like negative 3.72 times 10 to the 4, negative 4 meters. 4 would be crazy, meters, which is the same as negative 0.000372 meters, which is your distance away from the middle, from equilibrium in the negative direction, okay? And this is negative. Very quick piece on the Doppler effect, right? We have detector. Oops, let's make that a little bigger. We got detector and we got source. Detector can move towards source. Detector can move away from the source. The source can move towards the detector. The source can move away from the detector. Your sign in f prime is equal to f v v, same v, those two. Those are just the speed of sound in a given problem. Plus or minus v d plus or minus vs. Okay, sign is going to depend on which scenario you're in. For the detector, d toward s. If the detector is moving towards the source, positive v d. Detector is moving away from the source, negative v d. If the source is moving towards the detector, negative vs in the denominator. If the source is moving away from the detector, positive vs. Okay, so the only reason I'm bringing this up again is because you have to have something resembling this on your note card. You want to remember this, because if your signs are messed up, what'll happen is basically what this does, f prime is equal to f times v plus blah blah blah. This is a ratio. This is a ratio that is going to alter f by some amount, right? Let's say in the numerator you have v plus vd. In the denominator, let's say the source isn't moving at all, and you just have v. Well, if v is typically on the order of like 300 meters, and you have like 300 plus, I don't know, 5 meters per second, this is all in meters per second, over 300, and that's the speed of sound, again, in the given medium, pretending it's 300. Well, what's 300 plus 5 over 300? It's like 1.0 something, 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 right? So all you're doing is f prime then is equal to f times like 1.01 or something. So f goes from, let's say it's 80 hertz, it might jump up to 80.5. I don't know, depends on f. So if f equals this, f prime is equal to that. All right, so you're altering it, and that ratio is literally going to determine the frequency that the detector hears, or the frequency that you're talking about, given the formula. So it's very important to have your signs down. Definitely have something similar to that. The detector and the source can both move, and how that ratio is going to calculate will depend on how you set up the problem. So have that down. And typically, it's just the language of the problem that's going to determine which scenario you're in. If you have a bird flying at a mouse, well, the problem might ask you, okay, what does the bird hear when the mouse, I don't know, screams? Or what does the mouse hear when the bird is like flying down at it and, I don't know, screeching? Either way, you're going to have different situations. So pay very close attention. You're going to need reading comprehension to get which situation you're in. So when you're on the exam, take a second to read the problems. And this is just going to apply in general. I'm literally writing it down. Read the friggin' problem. Okay? Especially because I'll let you in on a little secret, right? Professor Glenn is not going to do this. He's not going to take problem, I don't know, 20 from the homework and just put it on the exam, right? You know what's going to happen is he's going to take problem 20, he will change a sign, he will change the direction, same thing. He will change certain numbers or the situation that you're in, and then he will put that on the exam. So, yes, the homework is a good reference for what to expect, but it's not 1-to-1 with the exam, right? No. Okay? Use the homework as a good reference for how these problems are going to be written, but not as a 1-to-1 indicator of what's on the exam. Very important point. I went off on a tangent, but it's good to keep this in mind. There will be different properties on the exam than there are in the homework. You'll be equipped with the formulas you need, but you will need contextual understanding. So read these problems when you're on the exam. It's going to be a little stressful because, it's your first Physics 2 exam, but definitely clear your mind. Just try and sit down. Just pay attention to what the problem is asking you and to the tools you have at your disposal. You will have a decked out note card, so you should be ready to tackle it, but don't just jump in with a formula. Try and think about what the problem is asking you. And that's my little tip for that.